now you've had a chance to kind of read this question and try to do it on your own and then discuss it in small groups. Let's look at this and see what kind of answer you get. Now, this is a little bit confusing because you already have the answer here, right? But on the actual exam, this is going to be electronic, okay? And so what they're going to do, when you take the practice exam, you'll actually do this. You'll click on it, and where you click on it, you can make this bar bigger or smaller, or make it disappear. And so you can make these bars any size you want. Is that clear? Yes? All right, so this is phenotype frequency, not genotype frequency, right? What does that mean, phenotype? What it looks like, right? Purple and long, right? Okay, so let's read through this, and I can tell you most kids don't feel bad if you got this wrong, because most kids get this wrong the first time they look at it. Even though we talked about linked genes, some kids don't think about what that means. You've done problems with linked genes, but somehow the way they ask this question confuses people. I don't know. But students conduct an experiment to test whether or not a trait for pollen shape and trait for flower color are next to each other. They cross two plants that are known to be heterozygous. Now, I think this is where people, this is it. This is where people get confused. Because as soon as they see that, what people assume, oh man, I hate when that happens. As soon as people see that, what they do is they assume that what you got is big P, little p, big L, little l, and that's what you're dealing with. But they ignore the first part of the problem that says they want to know if they're next to each other on the same chromosome. So rather than drawing it this way, what they should have done, what students should do, is actually draw it out, 2 chromosomes, because that's what you have, right? 2 copies of each chromosome. Remember us going through this over and over again, yes? Mm-hmm. Okay. So look here, you say long pollen shape is big L, is dominant over round, and purple is dominant over red. And then it says click on the value, so they would have you click here in that particular column to make the column pop up or not. That would be expected that traits are linked, and the dominant traits, now here's a key, another key phrase, and the dominant traits are next to each other, right, are next to each other on the same chromosome for both plants. How many people in here drew this out? Okay, no one. And this is a mistake that kids continuously make, and I keep begging you to draw these things out. So if you read this and you drew it out, what you would have done, I think, is you would have said, well, the dominant traits have to be on the same chromosome. That means big P, and what do I put here? Big L. Big L. So this is heterozygote, so what's on the other chromosome? Little p, little l. That's what you got. They're linked, which means we're going to assume there's no crossing over. Is that clear? We're going to assume no crossing over. So if they're linked, and how many different gametes do you have here? You only have 2. You can only make 2. If they were on different chromosomes, then you would have to do FOIL, right? You'd have to do big P, big L. Big P can go with little l, little p can go with big L, and little p can go with little l, right? But that can't happen here. Why? they're stuck together. They're on the same chromosome. They're linked. That word, when you see it on a test, you need to know what that word, that's a clue. That's a big clue. When they say either linked or next to each other on the same chromosome, that is a big deal. All right? That means they're going to go together. They move together from cell to cell. So that means if they're going to make gametes, one chromosome, the only gametes that they can make is big P, big L, or little p, little l. That's all they can make. And both parents are in the same situation. So you have big P, big L, little p, little l. So that gives you this, this, and this. So what does that end up being? That ends up being what? 75% what? Purple. That's right. I heard double dominant is correct. Purple and long, right? Yeah. And 25% what? Red and round. So that's why this is 75% purple and long and 25% red and round. You have to be careful with these linked genes. These linked genes will make a difference to your answer. If these genes were not linked, then you would do FOIL and you'd end up with a 9:3 to 3:1 ratio, right? So it depends. If you have two heterozygous parents, it depends. It changes. The problem changes if the genes are linked. That's the lesson from this problem. Make sure you have those notes, and when you review this, you're making sure you're remembering that the next time you see that. You could see a problem like this tomorrow on that Procore. I don't know. I don't look at the tests. Because I tell you that I don't want anybody thinking you're cheating, so you don't talk to each other, you don't look at each other's papers. When you're taking a test, I don't want anyone thinking I'm cheating, so I don't look at the test. I don't look at it, I don't want to touch it, I don't deal with it. There are no questions during the test. Is that clear? Either the end of course or the Procore. When we take a look at this one, they say, okay, here are these butterflies. There's white and then there's yellow. And we're only dealing with one gene here, so that's good. And they say white is dominant over yellow, right? Is that correct?
Yes.
So at this point, you know that this one's yellow and the other two are white. Is that correct?
Yes.
Because the homozygous recessive is yellow. So then they say the genotype frequency is this: big A, big A, big A, little a, little a, little a. Then they go on and they say, if a predator introduced to the butterfly habitat prefers the yellow trait, natural selection, right? What's going to happen? Yellow's going to die more than the others, yeah? So what would happen to the frequency here? It would go down. So no matter how you answer this, that whatever you do over here, this better go down. If this goes down, what happens to these two? They go up. One or the other or both go up. There's a little trick down here. Did you read it? There may be more than one right answer. There's more than one way to get this right. But there's some absolutely non-negotiables. Little a has to come down. How many squares do we have here?
2.
So isn't it neat you have 10? So each one of these boxes is 10%, right? And the other trick that they tell you, it's not a trick, it's a stipulation. It says you may use each butterfly more than once, but it also says, where does it say it? Assume all genotypes are represented. Did you see that? So you have to have little a in there. There have to be some little a's left over. All right, so answer A. Place the genotype that will have a higher rate of predation in the blank box for A. What would you put there? You say big A, little a. I'm going to read this again. Place the genotype that will have a higher rates of predation. What does higher rates of predation mean? They're going to eat more. So it's little a, little a. It's the yellow one. Right? So if you made that mistake, ask yourself, why did I not put little a, little a? I knew that. By the way, on the actual test, this will be electronic, and you'll actually click on this, and you'll move it over here. You'll actually drag it, click and drag. So don't panic if you see that. And you can move it more than once, as you see here. You'll be able to use them more than once. Is that clear? All right. The next thing says, place 10 butterflies in their habitat, create an approximate model of the genotype frequency change that would happen if, assuming that the predator is choosing the yellow butterflies more often. So each of these is 10%. This had to decrease, right? I had to bring this down. I'm limited. I can't bring it down by 9% because I only have one. I can only put one butterfly in a box, right? So I have to bring it down by 10%. I can't get rid of it altogether, right? Because it says, assume all genotypes are represented. So I have to put at least one little a, little a. Is that clear? As long as you did that, you're on your way to the correct answer. Then the rest have to be whatever you want. You can go big A, big A. How much are you going to increase the percentage of the other two? Probably by 10%. You add another one. So it used to be 3 of these and used to be 5 of these out of 10, right? So you can make 4 of these if you want, and you can keep these the same. You can only increase it by 1, right? Because that's all you got.
You got the same exact number.
Say that again. Or you could increase this one by another one. You could put little a, big A, little a one more time, right? It doesn't matter. It doesn't matter what happens here. What matters is that this is only 1, and you're increasing the others by 1, and you're ready to go. I don't care if you increase this by 1, the big A by 1, or the big A, little a by 1, because neither one of them is yellow. So either one could increase. Personally, I would increase the big A, because you're taking out little a's from the population. I'd go ahead and assume that I'm going to have more big A's, just to be safe. But it doesn't matter. Okay? You get, and you're both right. You see the bottom? There's more than one correct answer. Who got this right?
Me.
All right, so it looks like a lot of people got it right. If you got it wrong, it's okay. Ask yourself, why did you get it wrong? Do I understand this? If I don't understand it, what can I do to help myself? What you see here is you see do you guys want a minute to talk this over before we discuss it?
Yes.
All right, so go ahead and take a minute. Let's say 2 minutes and talk it over with each other. Understand this. Can I go to tutoring? Remember, this is for the OST, not for tomorrow, right? Tomorrow, what's tomorrow about? What is it about? Is it about you doing really well? No, it's about doing what? Growth, improving. Do your best. Do your best. You learned a lot all year long. Use that knowledge. Show it off. All right, guys. A computer program models the changing frequency of a single allele for 3 different population sizes. Each population program runs simultaneously, so for 50 generations, and it's charting what happens to that allele. Now, they say one allele, so it's either big A or little a, right? So it's all we're doing. It's only one, actually, so what's happening with big A? Is big A increasing or is big A decreasing, right? Is little a increasing or is little a decreasing? Whatever, right? So it's changing over time. And like you run it once, the blue line, it goes, oh, okay, that changed. The green line shows it changing, and the red line shows it changing over time. In this generation, there's less big A's, in this generation, there's more, and there's less. Do you see the change, yes?
Yeah.
And there's three, they run it 3 times. Which of these populations is going to change more over time? The smaller one will change more. So which one do you associate with which of these charts shows, 1, 2, or 3, which shows the most amount of change? 2. This shows the most amount of change. So which do you associate? The 30. Which shows the least amount of change?
3,000.
So where do you put that one?
3,000.
And then, of course, the last one must be 300. Yes?
Yeah.
And if they ask you to click on the graph that shows the greatest impact on the genetic variation because of genetic drift, which would you do?
Second one.
This one. And life is good. Easy, yeah? A lot easier than practice problems I gave you last night,
Yep.
right? And I think those are easy. And you'll see when we go over them. I think you'll agree once we go over them, they'll be easy. So I want you to continue working on those practice problems. I'm going to send you the answers probably tonight, if not tomorrow night. And once you can look at those answers. Tomorrow I will have for you a packet to do over the 4 days. All right?
Wait, what 4 days?
Thursday, Friday, Saturday, Sunday. All right, so we got 10 more minutes. You guys, let's go. Why don't we work on the problems? Let's start the Hardy-Weinberg issue problems then. Let's take a look at the Hardy-Weinberg practice problems. It says, we all got them out?
Yep.
All right.
No,
So-
not yet.
All right, hurry up.
We got to upload it.
Yeah, we'll have that later. All right. Let's do the first one. It says a population of rabbits. Could you read it? Because I'm kind of tired. Go ahead. Read the first
A
part.
population of rabbits may be brown, the dominant phenotype, or white, the recessive phenotype. Brown rabbits have a genotype of homozygous BB and BB. White rabbits have the genotype lowercase bb. The frequency of the dominant what the heck? Genotype is 0.35. What is the frequency of heterozygous zygotes?
So they tell you that BB is equal to 0.35. What is BB equal to in our equations? What are the two equations?
P plus Q equals 1.
All right. What's
Do you have any more copies of the
yeah? And what's the other equation?
P squared plus 2p cubed plus p squared equals 1.
Okay. So what is it that they tell me with big B, big B?
That is 0.35.
Yeah. And so what does that tell me? What does it? What in reference to the formulas? What does that tell me? What's equal to 0.35?
P.
P or P squared? Which is it?
P.
No, P squared. Remembering that these are your genotypes. So this is big B, big B. This is big B, little b, and this is little b, little b. This is the frequency of big B. This is the frequency of little b in the total population. Do we understand each other? Think about it. If you have 3 genotypes, you have to have 3 formulas to find those genotypes. This equation only gives you 2. This is for the alleles. Gosh, this thing's not working. And this is for the genotype. Are we clear? 1, we got it? All right. So we know that this is big B is 35%. What is it? Which one is 35%? Which is what? Which one? P squared equals 0.35. So how does that help me? How am I gonna, what's my next step? What am I trying to find? What's my question? You have to find, you're saying you have to find P, but oh, that's right, you're right. But what is it I'm trying to find? Is what's the frequency of the heterozygous rabbits? I'm trying to find this one, right? And to find that one, I need P and I need Q, right? Because the only way I'm going to find big B, little b frequency is if I have 2PQ. I have P squared. If I take the square root of both, what do I have? I have P, because they cancel. Square root of a square is a number, right? And so what's the square root of 0.35? 0.59. And there's my P. There's one answer for that I need. I'm gonna go ahead and notice I'm using colors. You won't be able to use colors on your scrap, but you can always put it aside and square it off. I doubt that on the end of course exam they're gonna have you calculate this. But it's good practice, as you saw, right? You saw the Hardy-Weinberg problems you just did. Knowing this really helps you, doesn't it? So 0.59 is P. How do I find Q? Because I still need Q. I got P, I need Q. That's right, P plus Q equals 1. If P is 0.59 plus Q equals 1, so Q therefore is equal to 1 minus 0.59, which is what? Q equals what? 0.41. So then the frequency of the heterozygote is 2 times 0.59 times 0.41, which equals what? Somebody want to do the calculator work on that? What's the frequency of the heterozygotes? 0.48. So that gives me big B, little b frequency. That's great, 48%. I know big B is 35%, so that's really helpful. So there's kind of three big ones. I got the big B frequency. I got the big B, little b frequency. I got two choices now. If I have a calculator, I'm probably going to choose the first one. I need to find, what's the last one? The question they ask you is, what's the frequency of the B allele? That would be Q. All right? And we already found that, didn't we? There it is. So if you know what it is, if they ask you what is the frequency of the white rabbits, then what would you do? If they asked you what's the frequency, they didn't ask you the frequency of the white rabbits, did they? They asked you the frequency of the B allele. What if they asked you the predicted frequency of the white rabbits? What would it be? There's two ways of doing it. The easiest way is right in front of you. 0.41 is not the frequency of the white rabbit. You square it is correct. You take Q squared, remembering that these are the genotypes. It's the Q squared that is the genotype for the little b. That is the white rabbit. A white rabbit has two genes, two copies of every gene. We know this, do we not? So we need that square. It's 0.41 squared. That would be the frequency of the white rabbits. The frequency of the allele, this little B allele, is 41%. 41 squared is the frequency of the white rabbit. Do we get this? Yeah. All right, so let's move on to the next problem then. Hypothetical population of 10,000 humans, 6,000. So we got a total population of what? Notice I'm starting to write it down right away. 10,000 total. and they're people, so I know they have 2 copies of each gene. 6,840 individuals have AA. 2,860 have AB. And 300 have BB. Now, what is the frequency of each genotype in the population? Now, this one might have thrown some people because there's no recessive, right? But here's the thing. When you're dealing with 2 of them, 2 options, notice this is heterozygote. This is homozygous of one. This is homozygous of the other. The math is still the same. Okay? Because p squared or q squared, it doesn't matter. If you're only dealing with A or B, if you're only dealing with 2 possibilities, then p plus q is still equal to 1. Right? And p squared plus 2pq plus q squared is still equal to 1. So they're both, you're still good. You can still use it. So what's the frequency of each genotype in the population? Well, that's easy to do. You don't have to do it. You don't have to do this at all for the frequency of each genotype, but you could if you'd like to. What's the frequency of big A, big A? What's the total? 10,000. So what's the frequency of the big A, big A? 6,840 divided by 10,000. What is it? 0.68. 68 or 684 if you want. 68, about 68.4%. That's for big A, big A. And this is what I'm saying. This is exactly what I'm talking about. It doesn't matter. It's that one thing that's going to end up messing you up on an exam. You don't, I mean... So there's 10,000. What's the answer there? 0.286. So about 28.6%. And for the big B, big B? Point what? 0.03 or 3%. All right, so if you want to find the percentages, you'd multiply times 100% each of these. That's all. Multiply times 100, there's your percentages. No big deal. So there's your frequency of each one. That was a simple answer, especially if you have a calculator. What's the frequency of an A allele? So AA, you can pick one, doesn't really matter, but you say, hey, that's p squared. This would be what then? If this is p squared, what's this one? Q squared. And so what's this one? 2pq, right? And they're asking, what's the frequency of the A allele? You have to do what? To find the A allele, what are you going to have to do? Always go. Sorry. All right, so you go with the square. You're going to do what? How do you find the frequency of the A allele? What's the square root? If you have the A allele is what? P squared is equal to what? How do I find, I do what? Square root. And what do I get? What do I get? What is it? I can't hear you. What's the square root of 0.68? 4.
0.684.
Point what? 83. So the A allele is 83%. What's the frequency of the B allele? It's Q squared equals 0.03. Q would equal the square root of 0.03, which is what? What is it? 0.17, 17%. Do those two equal 1?
Yes.
So I can check my work, right? I say if these two equal 1, then I'm on the right track. Next, if the next generation contained 25,000 individuals, how many would have the blood type BB, assuming the population is in Hardy-Weinberg, which means the frequencies don't change, right? And BB's frequency was what? 0.03. So what would you do? You'd take 25,000 individuals and multiply it times what? 0.03, and that's going to give you how many you have with a big B. Big B, what is it? 0.03 times 25,000. What is it? 750 individuals have that population, have that genotype. So it's really simple math. It's just percentages and those two equations over and over again. All right. Good luck tomorrow. Question 3 goes, a population of birds contains 16 animals. So there's 16. And of course, we're taking 16 red tail and 34 animals with 34 blue tail. The blue tail feathers are dominant. I'm doing 3. Blue tail are dominant, so this could either be big B, little b, or big B, big B. These are what? What is it? Our favorite up here? Our favorite up here is the red tail. Why is there, what? You're not listening. Some of you are talking now. Red tail, what's it, why is the red tail our favorite?
Because it's the homozygous.
Homozygous recessive, so it's little b, that we love these because we know what they are. These down here could be big B, little b, or big B, so it's a little confusing when we're dealing with incomplete dominance or codominance like we did with number 2. We don't have that problem, but when we have dominant recessive, the dominant can hide the recessive. What is the frequency of the red tail? That's easy to tell. What is it? What's the total?
50.
Total's 50.
Oh, 50.
So what's the frequency of the red tail? Yeah.
0.32.
16. That's right. 32%. Somebody says correct. 0.32. What about the blue tail? What's the frequency of the blue tail? 34 divided by 50. 0.68, so 68%. So that's easy to tell, and we're all good. Now, what does this tell us? What is the frequency? This doesn't tell us much. This doesn't tell us much. Why? Because this is a combination of both the heterozygous and the homozygous dominant. But this one tells us a lot, doesn't it? What does this equal? The frequency of what? The red allele, which little bit. It's not the frequency of the red allele. It's the frequency of what?
The red tail.
The red tail. Good. Which means what? It's the frequency of what?
The homozygous recessive.
Homozygous recessive. The frequency of little b, which is called what? In our equations, what are they called?
Oh, Q.
It's Q, now Q.
Oh.
It's squared.
Q squared. Q squared. It's Q squared.
Which one is that one?
Let's go over it one more time. You guys, this is what you have to study. This is what you should have in index cards, right? We know P plus Q equals 1. That's all the alleles. P and Q are all the alleles in the population. Those are alleles. That means all the big B's are here and all the little b's are here in this equation. If you want to talk about how many genotypes you have to talk about P squared plus 2PQ plus Q squared equals 1. And there you have to remember that the blue-tailed are going to be, the blue-tailed homozygous are going to be big B, right? And that's P squared. The 2PQ are the big B, little b. And then the red-tailed are going to be little b, which is the Q squared. You got to remember that. Or otherwise you'll be confused. All right? So you know Q squared is equal to what? 0.32. So what do I do? How do I solve for that?
You gotta do the square root of
I gotta do the square root of Q and the square root of 0.32. What's the square root of Q squared? All right, and what's the square root of 0.32? Do it. What is it? 0.57. Easy as pie. So you know Q squared. Say that again. Oh, somebody told me. I can't do square root in my mind like that. Some people can, I can't. Yeah, there are people that do it. I don't know how. There's a system to do it. I never learned it. And then some people are autistic and they memorize these things as well. But other than that, that's all I know. So Q squared, 0.57.
And then you put it into the first equation, the P.
And that's right, good. So then you take Q and you take P plus Q equals 1 and you put Q 0.57 into the equation. You get P equals what? 0.43. Oops. So P equals 0.43, Q equals 0.57, but they want to know what? What is it they want to know? What's the question? Somebody read the question out loud. We got the red allele frequency. Do we have the blue allele frequency? Yes, we do. Here's the red allele frequency here. Here's the blue allele frequency here. So we got those two. What about the frequency of the heterozygote?
Oh, we don't got that yet.
How do we find it? Guys, look up on this board. And where do you see the heterozygote?
In the 2P.
2PQ.
Oh, we got to.
All you got to do is do 2PQ. It's right in front of you. If you guys memorize this and understand it, it's not just memory, it's understanding that big B or homozygous dominant is there, homozygous recessive is there, and heterozygote's there, and then this is the frequency of the allele, the blue allele in this case, big B allele. This is the frequency of the recessive allele. If you understand that, there's no question they can ask you about this that you can't figure out. So, because it's not that hard. It's just simple algebra. So what's the frequency of the heterozygote? The frequency of the hetero,
It's 0.49.
which is big B little b, is equal to 2PQ, which is equal to 2 times 0.57 times 0.43, which I'm hearing is equal to what?
49.
Point what?
49.
0.49. So the answer is 0.49, so the frequency of the heterozygote is 0.49. The next question is, what's predicted frequency of the homozygous recessive? kind of a trick question, but. Oh, I'm reading the wrong, I'm sorry, I'm reading the wrong question, that's fine. What is the frequency of the bird's homozygous for the blue allele? So big B. What do I do? P squared. Big B frequency equals P squared. P is 0.43, so you square that is what? What is it? 0.1849, or you can round it off to point what? 19? 18? All right, let's do 18. As long as you're consistent, it really doesn't matter where you round it to. There's always going to be error. Are we good? That's it. You answered number 3. See how easy that was? It's not really isn't that hard. Your hard part is, wait, what's homozygous? What's number 4? Number 4 says brown hair, big B, is dominant over, let me get, brown hair, big B, is dominant over a blonde hair, little b. All right. I will be asking you to upload these notes at the end of today for your first quiz of this 4th quarter, just for you to know. So we're going to stop in 5 minutes, so you got time to upload it. You can, but you will be uploading before you leave this class. It's okay if you have it unwritten on there. I just want to see that you've been paying attention. So if there are 168 brown-haired people, 168 brown-haired people, so big B blank equals 168. And there's in a population of 200, so that's out of 200. What is the frequency of brown-haired people, by the way? What is it? 84%. But that's brown-haired people. It doesn't really help us because we don't know what that second allele is. Now, if we have 168 brown-haired people, what we want to know, though, is the blonde people. How many blondes do we have out of 200? 32. Where did we get 32? It's 200 minus 168, right? So they're either brown or they're blonde. You have to assume it. I guess you could have redheads, but it's not part of the problem. So you got 32 out of what? 200. So what's the percentage there? 16%. So now we got what? What is this? This is very helpful. This is your best friend. What's little b? Little b? Q squared. So recessive is correct. It's Q squared. So now we know what Q squared is 0.16. I'm going to get rid of the percentage. I'm going to go ahead and make a change and say 0.16. It's the division. 32 divided by 200. Okay? I know it's at an angle. Say what? Oh, this little line? This just it's just so I can differentiate it between 9 and Q. It's a good way for me to do it. It's a European Q, they call it, whatever. So 16%, and I'm going to go ahead and change this 84 to 0.84, just so everybody sees that. This is actually not a very useful number, but we did it. So Q squared is 16. Then they ask a question. What is the predictive frequency of the heterozygotes? So what is the frequency of big B, little b? It is not the same. What do we got to do? We have to find both the recessive and the dominant, and then we have to plug them in. So what are our two equations? Equals 1, and the other one is? So now we got these two equations. We got Q squared, so we got that. How can we find P? Square root. I heard someone say it's correct. You take the square root of both sides here. So that would mean that we're now talking not about Q squared, but about what? .04. 0.04 is Q, so
It's 0.4.
it's 0.4, I'm sorry. Thank you.
Oh.
0.4, so it's 0.4 is Q. What's P?
How do we know that's 0.4, bro? Because we got equal 1.
Because it has to equal 1.
1 minus 0.4.
So 1 minus 0.4 is 0.6. That's all right. It's a good question. So it's 0.6. So that means 60% of the population of the alleles in this population are big B, and 40% of the population have a little b allele. All right, 40% of the alleles in the population are little b. Okay. That tells us the allele, but that's still, we still haven't figured this answer out. This is the one we want. How are we going to figure that out? Plug it in. How? Plug it in where? Where am I looking for this? This one? This term?
No, you look at it for the head.
This right. This one. The one for the heterozygous. Good. You got this, don't you? You're going to get an A on this test. So you're going to go 2. What you're going to do is you're going to figure out 2 PQ. And that's 2 times what? 0.4. Well, it's 0.6, but either way, it doesn't matter. But I'm going to go ahead and just say it. Keep it straight. It's 0.6 times 0.4, which equals what? 0.48. So it's 48% of the population are heterozygote. So that's the answer there. What's the predicted frequency of the homozygous dominant? That's big B, big B. What is big B, big B? So remember that I'm gonna say it again. This is your big B, little b. This is your little b, and this must be your big B, big B. So how do I find big B, big B? It's 0.36 because you take P and you square it, because that's P squared. You see, big B is P squared. So it's 0.6 squared, which is equal to 0.36. So it's 36% of the population.
Wait, how you do that? Well, you have to put percent or the decimal.
Well, when I see the decimal, I think percent, right? You can say 0.36 out of 1, or you can say 36%. Doesn't matter. Now the question is, where did I get 0.6? Guys, this equation is the frequency of each of the genotypes in a population. The frequency of big B is P squared. We figured out P by subtracting Q. And that got us 0.6. Square it, you got 0.36. Take 0.6, put square on your calculator, you'll get 0.36. That's how we got this. All right, so we'll finish this in the next class. Make sure, yes.